Okay, at the previous lecture we introduced the Fourier transform on the real line, and we stated some of its basic properties without proof. Well, let's recall the construction. If f is an integral function on the real line, then we define its Fourier transform to be a function of f hat, also defined on the real line. So it is defined on the same group for the simple reason that R is self-dual. So the dual of R is identified with R. So f hat is defined on the real line by the following formula. So this is the Fourier transform of f. We observed at the previous lecture that this function of hat is actually continuous and vanishes at infinity. This is so-called Riemann lemma. So we have a map, f of script f, which acts from 1 of R to C0 of R, and it takes every function f to the Fourier transform f hat. And this map is linear and it is bounded because it's more or less obvious that the supremum norm of f hat is less than or equal to the L1 norm of f. So as a result, this is a bounded linear map. Actually, when we proved the Riemann lemma, we essentially used the fact that this map is continuous. We first observed that f takes characteristic functions of intervals to functions in C0, and since the characteristic functions span dense subspace of L1, it follows by continuity and by the closedness of C0 that C0 is closed in the space of all bounded functions, and so this implies that f indeed takes a 1 to C0. Also, I recommended you to do this for exercise and to show that f is actually an algebra homomorphism. If we equip L1 of R with the convolution multiplication, then we have the following formula. The Fourier transform of the convolution is the pointwise product of the Fourier transforms. So it is an algebra homomorphism. The range of this homomorphism is, it has a special name. It is usually denoted by A of R. So it is a subalgebra in C0 of R. And it is called the Fourier algebra of R. Another useful exercise is to show that Fourier transform is not surjective. So this algebra this is a proper subalgebra in C0 of R. And at the end of the previous lecture, we discussed, we stated without proof, some basic properties of the Fourier transform. The first basic property is the uniqueness theorem, which means that the Fourier transform is injective. The Fourier transform is injective. Second, then we have the density theorem, which states that the range of L1, the image of L1 under the Fourier transform, that is the Fourier algebra in our terminology, is dense in C0 of R. And one of the most fundamental results is the Poincaré theorem. The Poincaré theorem. Which states roughly that the Fourier transform can be also defined on L2. This is not an exact statement because formally we cannot substitute a function from L2 to this formula. If f sits in L2, then the integral doesn't exist in general. Nevertheless, the theorem states that if we restrict the Fourier transform to the intersection of L1 and L2, So this is a proper subspace of both L1 and L2. Then it takes this intersection to L2. And moreover, this restricted Fourier transform, the Fourier transform restricted to the intersection of L1 and L2, uniquely extends to a unitary isomorphism, from L2 onto itself, which will be denoted by F dot. And moreover, F dot squared is just the antipode map S, which takes function f of t to f of minus t. And finally, we have the inversion formula. The Fourier inversion formula. Which is actually closely related to this one. And it states that if f is an integrable function, then its Fourier transform is also integrable, if and only if f sits in the Fourier algebra, or more exactly, if there exists a function of 0 in the Fourier algebra such that f is almost everywhere equal to f0. So these two properties are equivalent. And if these properties hold, then f0 can be reconstructed from the Fourier transform of f by the following formula. So we apply the Fourier transform twice, which is reasonable because f hat is also assumed to be integrable, and apply the antipode and obtain f0. So in other words, this means that we have the following formula: f of t is almost everywhere equal to f hat of t, and this can be reconstructed from f hat as follows: f hat of lambda 2 pi I lambda t 0. Okay, so these are the basic properties of the Fourier transform on the real line. There are several ways of proving these results. I'd like to show you the ingredients of a proof which is, in my view, the optimal one, and which is essentially due to Laurent-Schwarz. Or roughly, the idea of the proof is to extend the Fourier transform to a much bigger space, which consists of tempered distributions on the real line. So here are the main ingredients. First of all, we need the following standard lemma, which you probably know from your calculus course, and which relates the Fourier transform to the derivative. If f is continuously differentiable, a continuously differentiable function on the real line, and both f and its derivative belong to L1, so they are integrable, then the Fourier transform of the derivative of f is related to the Fourier transform of f by the following formula: 2 pi I lambda f hat of lambda. If we now iterate this property, we come to the following result. If f is p times continuously differentiable, and f together with its derivatives up to fp, all of them are integrable, Then we can apply this formula several times. And finally, we get a relation between the Fourier transform of the pth derivative of f and the Fourier transform of f itself. But we already know that the Fourier transform of f vanishes at infinity. And this implies that the Fourier transform of f, okay, so we know that this is for the Fourier transform of f and also for the Fourier transform of the derivative, and for the Fourier transform of the pth derivative of f. And since the Fourier transform of this function vanishes at infinity, this implies that actually the Fourier transform of f itself decays at infinity faster than lambda to the power minus p, as lambda goes to infinity. Property 3 is in a sense dual to property 1. If we assume that f is integrable, and if we multiply f by the coordinate function t, if this function is also integrable, where t is just the identity map of the line, then the Fourier transform of f is continuously differentiable. And the derivative of the Fourier transform is minus 2 pi I times the Fourier transform of the function tf. And again, we can iterate this and obtain the following property. If the functions f, tf, and so on up to t to the power pf, if all of them are integrable, then f hat, the Fourier transform, is p times continuously differentiable. All these results are proved, well, actually 1 and 3 are proved by straightforward calculations and by some properties of the integral. 2 follows from 1 and 4 follows from 3. So roughly properties 2 and 4 mean that the smoother function f is, the faster f hat decays at infinity. Yeah, the other way around. And these observations led Laurent Schwartz to the idea that the Fourier transform must be exceptionally well behaved on a certain proper subspace of L1, the so-called Schwartz space. The Schwartz space is defined as follows. The Schwartz space on the real line is the following vector space, which is denoted by script s of r, and it consists of those infinitely differentiable functions f on the line, such that for all non-negative integers k and l, t to the power k times the elf derivative of L is bounded. So roughly this means that f is a function of rapid decay at infinity. It decays faster than 1 over every polynomial, and the same is true for all derivatives of f. The Schwartz space has a natural topology. We can define a family, a countable family of seminorms on the space as follows. So for every k and l, we just take the supremum of this function over the line, and we get a seminorm on the Schwartz space. And if we consider the family of all such seminorms indexed by pairs of non-negative integers, then this family determines, so this leads to a topology on the Schwartz space. And we get the following, and we have the following theorem. The theorem states that the Fourier transform takes the Schwartz space to itself, and if we restrict the Fourier transform to the Schwarz space, then this is a topological isomorphism of the Schwarz space onto itself. And moreover, f squared is equal to s. F squared is equal to s on the Schwarz space. Where again, the operator s is defined by the same old formula. It takes f of t to f of minus t. Well, I will give you all the details of the proof, but instead I'll divide the proof into several sub-exercises which are not very hard, and I hope you will be able to reconstruct the details. Well, lemma exercise 0 is actually, it is not about the Schwarz space and not about the Fourier transform, but it's just it's a standard criterion of continuity of a linear operator. You will have two vector spaces, say E and F, and each of them is equipped with a family of semi-norms. So suppose that P is a family of semi-norms on families of semi-norms on E. And Q is a family of semi-norms on F. Let's denote them in this way. So these are families of semi-norms. On E and F, respectively. So we equip E and F with the topologies generated by these families. And suppose that T is a linear operator from E to F. Then I claim that T is continuous, even only if it satisfies the following condition for every J in this second index set, that is for every semi-norm from the family of semi-norms on F. There exists a constant C, positive constant, and there exist finite and many semi-norms from P, from the first family, such that for every vector V in E, we have the following estimate. So this is a useful continuity criterion for a linear operator acting between two vector spaces topologized by families of semi-norms. In fact, this is a straightforward, generalization of the well-known fact from functional analysis that a linear operator between normal spaces is continuous if and only if it is bounded. Lemma exercise 2, lemma exercise 1. This was 0, now lemma exercise 1. Let's introduce an auxiliary operator, F. Let's denote by F hat the composition of F and S. Or, by the way, we can write also them in the opposite order because they commute. So I claim that first of all, the Fourier transform takes the Schwarz space to itself, so we have the following inclusion. And moreover, F together with F hat are continuous. F and F hat are continuous maps from the Schwarz space to itself. Well, the best way to prove the continuity is just to apply this. To apply lemma 0. And this inclusion together, by the way, the continuity itself, is based on these properties of the Fourier transform. Okay, now lemma exercise 2. Lemma exercise 2. introduce two operators. We define two operators M and D on the Schwarz space as follows. M is just the multiplication by the coordinate by T, and D is the derivative divided by 2 pi I. Then I have the following relation. Fd equals mf, and fm equals minus df. Well, actually, this is nothing but our first lemma, which is still here. So basically, this is equivalent to properties 1 and 3. Just a restatement of 1 and 3. Lemma exercise 4. Oh, lemma exercise 3. Well, this is an immediate corollary of lemma 2. So let's define T to be the composition of f hat and f. Well, first of all, I claim that these two operators commute, f and f hat commute, so we can also write T as a composition of f and f hat. And this operator T commutes with D and with M. This is almost immediate from lemma 2, applied first to f and then to f hat. Well, why is it useful? This is useful because these two properties actually imply that T is almost the identity map. Lemma exercise 4. Suppose we have a linear map from S to itself, linear map, such that it commutes with M and with D. Then T is the identity map times a suitable constant for some constant C. Well, let me give you a little hint to this exercise. For every number A, we can introduce the following subspace MA, which consists of various functions in the Schwarz space, which vanish at A. Now, the fact that T commutes with M actually implies that T takes each such subspace to itself. So all these subspaces are T invariant. And this is true for all A. And this property in turn implies that T is actually the multiplication by a smooth function. There is a smooth function C on the real line, such that T is the multiplication by C.
How it immediately follows?
I don't say this immediately. This is a little exercise. A little exercise for you. This is not very hard. Now, what we also know that T commutes with G. T commutes with G. And since we already know that T is of this form, and since it's commutes with G, we can deduce from here that C is actually a constant. Okay, so this is a hint to exercise 4. And finally, lemma 5, lemma exercise 5. So actually what we want to do, we want to show that C is equal to 1. This will complete the proof. And to show that C equals 1, let's consider the following concrete functions. The following concrete function, given by the following formula. And I claim that the Fourier transform of f is equal to f. Again, here's a little hint. Again, there are several ways of proving this. In my view, the shortest way is to show that both f and f hat satisfy the same differential equation. Namely, we see from this formula that f satisfies the following relation. This is more or less clear from the exact formula for f. But if we now use the properties of the Fourier transform, I mean the properties given in this lemma, we easily deduce that f hat satisfies the same differential equation. So but this is a first order linear differential equation. Its space of solutions is one-dimensional. So this implies that f and f hat can only differ by a constant, a multiplicative constant. And to show that this constant is equal to 1, we simply evaluate at 0. F of 0 is 1. And on the other hand, it's a standard fact that f hat of 0, which is just the integral of this function, is also 1. So as a result, we see that C equals 1. Now, actually, this is not a hint, but actually this is a complete proof of lemma 5. Okay, so combining all these lemmas, we get the proof of our result. We see eventually that T is the identity map, and so this means precisely that f and f hat are inverses to each other. And so in particular, this implies that f is a topological isomorphism of S onto itself. Why is it useful? This is useful because this enables us to extend the Fourier transform to a much bigger space, which is usually denoted by S prime of R. And this is just the topological dual of S. That is, this is the space of all continuous linear functionals. Continuous linear functionals on the Schwarz space. This space is called the space of temporal distributions. Space of temporal distributions. I will not explain the terminology at this point. This is not so essential for our purposes. And also, I'll not really call you what a distribution is. But for us, for our purposes, this space is useful because we can easily extend the Fourier transform to this space. Well, the Russian for temporal distribution is the usual terminology is обобщенные функции умеренного роста. First of all, let's observe that the space is indeed very big. Which is also a simple exercise to show that if P is a real number between 1 and infinity, possibly P is infinite, this is also possible, then we have an inclusion of LP into the space S prime of R. given by the following formula. If f is a function in LP, then the respective functional on the Schwarz space takes every function phi from the Schwarz space to the integral of the product f phi. And this is indeed an injective linear map. So yes, we see that S prime, the space of temporal distributions, contains all LP spaces. So it is big. We now extend the Fourier transform to the space of temporal distributions as follows. We gave one more notation. We define f prime from S prime of R to itself by the following simple formula. It takes G to G composed with F. So in other words, f prime is just the dual map to the Fourier transform. F prime is dual to F, which acts from S to itself. And we call f prime the Fourier transform on S prime. The Fourier transform of temporal distributions. We already know that f itself, when we consider f as a map from the Schwarz space to itself, we know that f is a topological isomorphism of S onto itself. And this really implies that f prime is a vector space isomorphism. F prime is an isomorphism of S prime onto itself. In fact, it is also a topological isomorphism if we suitably topologize on the space of temporal distributions. Well, this is not necessary for our purposes, so we consider S prime as just as a vector space. This tool almost really implies all the basic properties of the Fourier transform. So this is our final exercise about this, which easily gives us the proofs. First of all, let's look at the following diagram. We have the Fourier transform on L1, which takes L1 to C0. Well, L1 is embedded into the space of temporal distributions by means of this formula. And the same formula gives us an embedding of C0 into S prime. And here we have F prime. So now a straightforward calculation shows that the diagram commutes. This is a straightforward calculation based on Fubini's theorem. But since F prime is an isomorphism, this really implies the uniqueness theorem, the injectivity of F. Exercise 2. Let's now look at another commutative diagram. So we have the Fourier transform on the Schwarz space, which is a topological isomorphism. The Schwarz space is contained in L1, and at the same time it is contained in C0. And here we have the Fourier transform on L1. And just by construction, this diagram commutes. But now one can prove that the Schwarz space is dense in C0. The Schwarz space is dense in C0. This is an exercise for you. And if we combine this with the bijectivity of the Fourier transform on the Schwarz space, we see that the Fourier transform has a dense range. Simply because the upper horizontal arrow is bijective, and because S is dense in C0. So we have the density theorem. And a similar argument can be used to prove the Poincaré theorem. Again, we have the Fourier transform. We start with the Fourier transform on the Schwarz space. We embed the Schwarz space into L2. And we do a little calculation again, based on Fubini's theorem, which shows that the Fourier transform on the Schwarz space is actually a unitary operator with respect to the inner product induced from L2. So if we consider the Schwarz space as an inner product space, an incomplete inner product space with inner product inherited from L2, then this is a unitary map, a unitary isomorphism. But a unitary isomorphism between dense, from a dense subspace of Hilbert space to itself, uniquely extends to a unitary isomorphism of this Hilbert space onto itself. So as a result, we get a unitary isomorphism here. This is not yet the Poincaré theorem itself, because this diagram shows that if we first restrict F to the Schwarz space, then it can be extended to L2. But the Poincaré theorem also states that this map, if we restrict to the intersection of L1 and L2, then we have the classical Fourier transform. But why is it so? Well, let's complete this diagram as follows. L2 is embedded into the space of temporal distributions. And here we have F prime. And again, a little calculation shows that this diagram also commutes. So as a result, we see that F prime extends both F dot, which is defined on L2, and the classical Fourier transform defined on L1. And that's it. This shows that F dot and this Fourier transform agree on the intersection of their domains. And this is exactly the Poincaré theorem. And finally, the inversion formula can be proved along the same lines. So this is also an exercise here. So in summary, we see that by using the Fourier transform on temporal distributions, we can deduce all the basic properties of the classical Fourier transform on L1. Okay, so that's what I wanted to tell about classical harmonic analysis on the real line. So now our next strategic goal will be to extend all these results to arbitrary locally compact abelian groups. So to begin with, let's recall some standard facts on locally compact spaces. Locally compact spaces and Radon measures. First, let's recall the following standard definition. If we have a topological space X, it is locally compact. Locally compact if for every point X in the space there exists a neighborhood U of X such that the closure of U is compact. The closure of U is compact. Here are some basic examples of locally compact spaces. Clearly, all compact spaces are locally compact. It's also clear that all discrete spaces are locally compact. In this case, we can just take U the set consisting of X itself, a single point set. Rn is obviously locally compact. And more generally, every manifold, any C0 manifold, any topological manifold is also locally compact. Let's also look at some non-examples. That is, topological spaces which are not locally compact. Maybe a simple non-example is, the simplest non-example is the space of rationals equipped with the topology induced from the real line. It's easily seen that it is not locally compact. Next, it's a standard fact of functional analysis that if we take an infinite dimensional normed space, then the unit ball in the space is not compact. Now, this easily implies that an infinite dimensional normed space, is not locally compact. Also, and this is a simple exercise for you, if we take the product of infinitely many non-compact spaces, then we get something which is not locally compact. An infinite product of non-compact spaces. This product is not locally compact. By the way, if you take a finite product, then everything is okay. This is also a simple exercise. The product of finitely many locally compact spaces is locally compact. A nice property of locally compact spaces is that there are many continuous functions on such spaces. More exactly, we have the following standard result, which is a version of the so-called Urson's lemma. Suppose that X is a locally compact Hausdorff topological space. And suppose that we have two disjoint sets, K and F, two disjoint sets in X, such that K is compact and F is closed. So Urson's lemma states that we can always find a continuous function phi from X to the interval 0, 1, such that phi is identically 1 on K, phi is identically 1 on F, and moreover such that the support of phi is compact. So this is a version of Urson's lemma. So traditionally, Urson's lemma is normally stated for normal topological spaces, but this one is easily reduced to normal spaces by taking the one-point compactification. Anyway, the proof can be found in any book on general topology. Okay, let's now discuss Radon measures on locally compact spaces. So from now on, we assume that X is a Hausdorff locally compact topological space. Well, let's introduce some notation. Let's consider the Borel sigma algebra. This will be denoted like this. The Borel sigma algebra on X, which is by definition the smallest sigma algebra of sets. The smallest sigma sub algebra of the algebra of all bounded of all subsets of X containing all open sets. Containing open sets. By definition, a Borel measure, or more exactly, a positive Borel measure, on X is a sigma additive measure, that's denoted by mu, on the Borel sigma algebra. But mu is not assumed finite, so it is possibly infinite on some sense. Now, today all Borel measures will be positive, so let me put this in brackets. Later we'll need also complex Borel measures, but today all Borel measures will be positive Borel measures. Well, since X is a topological space, it's reasonable to consider those Borel measures which are in a sense compatible with the topology. So we have the following definition. Suppose that mu is a Borel measure on X. And suppose that B is the Borel subset of X. We say that mu is, actually we'll have two definitions. Definition one, we say that mu is outer regular on D. If we can approximate it from outside by open sets, if mu of B is equal to the infimum of mu of measures of all open sets containing the B. In this case, we say that mu is outer regular on B. And property 2, we say that mu is inner regular on B if B can be approximated from inside by compact sets. If mu of B is equal to the supremum of measures of compact subsets of B. And finally, we say that mu is a Radon measure if it satisfies the following three conditions. Condition one is that the measure of every compact set is finite. For every compact subset K of B, K of X, sorry, X, the measure of K is finite. Property 2 is that mu is outer regular on all Borel sets. And finally, property 3 would require that mu is inner regular on all open sets. Well, let's look at two basic examples of Radon measure. Example one is the usual Lebesgue measure on Rn. It's a standard fact of measure theory, which is normally proved in any standard course of measure theory, that the Lebesgue measure is actually regular on all, inner regular and outer regular on all Borel sets. So it is a Radon measure. And another example is the counting measure of on an arbitrary discrete space. Suppose that X is discrete, so the Borel sigma algebra consists of all subsets of X, and the counting measure is defined by the whole simple formula. Is just the cardinality of A if A is finite, and plus infinity otherwise, if A is infinite. This is the counting measure. Well, it's easily seen that the counting measure is regular, outer regular and inner regular on all sets. This definition actually may seem a bit strange because at the first glance it would be much more natural to require that mu be outer and inner regular on all Borel sets, just like in this example. However, for technical reasons, it turns out that this is a bit too much to ask if X is an arbitrary, locally compact space. In fact, this definition defines an object which is, strictly speaking, this is an outer Radon measure. And there is also a dual notion of an inner Radon measure. In the definition of an inner Radon measure, we keep condition 1, we remove condition 2, and in condition 3, we require the inner regularity on all Borel sets. And it turns out that there is a one-to-one correspondence between outer and inner Radon measures, but in general, these conditions are not, these properties are not equivalent. Fortunately, all these problems disappear if X is nice enough. So we have the following two facts, which can be also done as exercises in measure theory. Fact 1, suppose that X is a sigma compact. Sigma compact, which means that X is a countable union of compact sets. Union of countable many compact sets. Then each Radon measure of X is inner regular on all Borel sets. So it is outer regular and inner regular on all Borel sets. Moreover, if X is second countable, suppose that X is second countable, that is, the topology on X has a countable base, which is also very normal and standard property, which is often satisfied in concrete situations. And suppose that mu is a Borel measure on X, which is finite on all compact sets, which satisfies this condition 1. Now this property alone already implies that mu is inner and outer regular on all Borel sets. Mu is inner regular and outer regular on all Borel sets. So actually coming back to the fact that the Lebesgue measure is inner and outer regular, we see that the only property of Rn, which is essential here, is that Rn is a locally compact Hausdorff space, which is second countable. So the standard proof of this fact for the Lebesgue measure of on Rn easily extends to an arbitrary second countable locally compact space. So in summary, we see that X is not very bad then the only thing to check is that the measure of every compact set is finite. This automatically applies the regularity property. By the way, the assumption that X is sigma compact, or the assumption that X is second countable, is quite natural. It is indeed satisfied in many concrete situations. And sometimes it can essentially simplify the proofs. So in all the cases where this assumption can indeed simplify the proof, we'll always assume that the locally compact spaces and the locally compact groups we're interested in are sigma compact, or if you like, second countable. So if this leads to essential simplifications, then we will always make this assumption. Okay, let's now recall a very important result about integration on locally compact spaces. First of all, we need the following notation. Let's denote by C sub C of X the space of all continuous compactly supported functions on X. Clearly, this is vector space. There is a natural order relation on the space. If f is a continuous compactly supported function on X, we say that f is positive, or if you like, non-negative, but usually we say positive, if it is everywhere non-negative. And now we have two functions in this space, f and g. We say that f is less than or equal to g if g minus f is non-negative. And finally, we denote by C plus of x the positive cone of the space, which consists of all non-negative functions f in C of x, such that f is non-negative. We now have the following definition. Suppose we have a linear functional I on the space of continuous compactly supported functions. We say that I is positive, and write the following combination of symbols. If it takes non-negative functions, two non-negative numbers. If this is positive, whenever f is positive. And here's an obvious example. Suppose that mu is a positive random measure. A positive random measure on X. We define a functional I mu on our space of continuous compactly supported functions by the following simple formula. This is just the integral with respect to mu. Then it's clear from the properties of the integral that this functional is positive. By the way, why is it defined? Well, it is defined for the following reason. F is continuous, so this implies that F is Borel measurable. The range of every Borel set is Borel. So F is Borel measurable. It is bounded, because it is continuous and compactly supported. And it is concentrated on a set of finite measure, because it is compactly supported. And the measure of every compact is assumed to be finite. And now it is standard fact of measure theory that every measurable bounded function, which is concentrated on a set of finite measure, is integral. So the integral is well defined. Okay, so this function is obviously positive, and we have the following fundamental result, which states that all positive functionals of this space are of this form. This theorem is usually attributed to Rees-Markov and Kakutani.
Sorry, do we assume that values of f are in R or what? Like how do we say that something is bigger than 0 if it's complex?
It can be bigger than 0, sometimes it is 0, but what's the problem?
Ну, какой у нас вообще порядок на c тогда?
Well, the order is very easy, very obvious. We say that a complex number is positive if it is real and positive.
If it's real, right?
Yeah. Of course, we can write if z is a complex number, we write z is greater than or equal to 0 if it is, by definition, if it is real and non-negative. So if it is complex, if its imaginary part is non-zero, then this condition is not. This condition fails. So of course we assume that it's real. Now there is Markov-Kakutani theorem, which is actually has a long history, and there are many other famous mathematicians which contributed to the proof of this result. It states that we have a bijection. We have a bijection between the set of all positive random measures, x, and the set of all positive clear functionals on the space of continuous compact and supported functions. And the bijection takes every random measure mu to the integral I mu. So this is very useful, and we will use this result fairly soon when we discuss the hard measure on locally compact topological groups. Okay, let's now discuss some basic facts on locally compact groups. Locally compact groups. First of all, by a topological group, we mean a group G, equipped with a topology such that the topology is compatible with the group operations, namely the group operation is assumed to be continuous for this topology, and the inversion map is also assumed to be continuous. Such that these maps are continuous. Let's make some straightforward observations, which are immediate from the definition. First of all, let's observe that for every x in G, the translation maps, the left translation and the right translation maps which take y to xy, and the map which takes y to yx, are homomorphisms of G onto itself. This is obvious because they are continuous one-to-one, and the inverse maps are also continuous because they are multiplications by the by x inverse. And also, this is observation 1. Observation 2 is that the inversion map is also a homomorphism. If you have two subsets, let's introduce some notation. If you have two subsets S and T of G, we define the product ST to be the set of all products of the form XY, where X runs over S and Y runs over T. And we denote by S inverse the set consisting of the inverses of all points in X. We say that a subset S is symmetric. If S equals S inverse. And we will often use the following straightforward observation. Let's observe that every neighborhood of the identity, every neighborhood U of the identity element in G contains a symmetric neighborhood. Contains a symmetric neighborhood of the identity. Well, indeed, why is it so? We can simply take the intersection of U and U inverse. Namely, the intersection of U and U inverse. So U inverse is also a neighborhood of the identity. And the intersection is clearly symmetric. This is obvious, but this is very, very useful. In particular, this implies that we have a base of symmetric neighborhoods of the identity. Well, arbitrary topological groups are too general objects for doing harmonic analysis. We are mostly interested in locally compact groups. And when we say a locally compact group, we always mean a locally compact Hausdorff topological group. A locally compact group is, by definition, a locally compact Hausdorff topological group. Well, let's look at some basic examples of such groups. Well, of course, all discrete groups are locally compact. In particular, the group of integers is locally compact because it's discrete. The real line and the multiplicative group of the real line, they are locally compact, and the same is true for the complex plane. The circle is locally compact because it is compact. The group of periodic numbers is known to be locally compact, as well as the multiplicative group of this field is locally compact. The group of periodic integers is, well, actually it is compact, so it is a compact topological group. Standard metrics groups are also locally compact. GLN over the real or complex numbers, and SLN over the real or complex numbers. They are locally compact. Well, GLN is locally compact because it is an open subset in the set of all matrices. And an open subset of a locally compact Hausdorff space is locally compact. And SLN is a closed subset of all the space of all matrices. And so this implies that it is also locally compact. More generally, well, this can be extended, of course. The unitary group is compact, and the special unitary group, the orthogonal group, the special orthogonal group, and there are many other examples. All these matrix groups are locally compact, and some of them are compact. And more generally, any Lie group, any real Lie group, is locally compact because it is a manifold. Okay, well, as for non-examples, we have actually two standard non-examples when we discussed log and complex spaces, namely the group of rationals is a topological group, but it is not locally compact. And the additive group of an infinite dimensional normed space is a topological group, but it is not locally compact. Let's now discuss uniformly continuous functions of topological groups. Suppose that G is a topological group, and suppose that F is a function on G. We say that F is left uniformly continuous and respectively right uniformly continuous. Uniformly continuous. If it satisfies the following condition, for every positive epsilon, there is a neighborhood of the identity, a neighborhood U of the identity element, such that for every x in G and for every little u in this neighborhood, we have the following inequality: f of x minus f of x u is less than epsilon. So this is the left uniform continuity, and for the right uniform continuity, we have required that f of x minus f of ux is less than epsilon. Well, clearly, if G is abelian, then these two kinds of uniform continuity are equivalent. But in the general case, they are not equivalent. The counterexample will be given in our next exercise sheet. Also, it's clear that if G is the real line, then we come to the usual uniform continuity, which you know from your calculus course. It's a remark. For the real line, we get the usual property, the usual uniform continuity. Well, the neighborhood of 0 is just an interval from minus delta to delta, so for every epsilon there is a delta, such that if the distance between 2 points is smaller than delta, then f of x minus f of y is less than epsilon. By the way, we can also write this property in the following equivalent form. Equivalently, f is left respectively right uniformly continuous if and only if for every positive epsilon there is a neighborhood U of the identity such that for all x and y in G satisfying the following condition, x inverse y belongs to U. This is for the left uniform continuity, and for the right uniform continuity we must take y x inverse belongs to U. So for all such pairs x and y, we have f of x minus f of y is less than epsilon. This is just an equivalent form of writing this definition. X, if this is y, this is y. If this is y, then x inverse y is just U, for the value which is in the neighborhood. And similarly for the right uniform continuity. So now it is really clear that for the real line we get the usual uniform continuity, because this property means that the absolute value of x minus y is less than delta. Okay. By looking at this definition, we see that it is somehow similar to the uniform continuity of a function defined on a metric space. Formally, these two types of uniform continuity are different. Well, I mean the uniform continuity on a topological group and the uniform continuity of function on a metric space. They are not special cases of each other. Actually, it turns out that both types of uniform continuity are special cases of uniform continuity on uniform spaces. Roughly, a uniform space is a topological space together with an extra structure which enables us to compare neighborhoods of different points, which is not possible in an arbitrary topological space. In a metric space, we can compare balls with different centers simply by comparing their radii. So this is bigger than this because the radius of this ball is bigger than the radius of this ball. In a topological group, we have two options of comparing neighborhoods of different points. To compare neighborhoods of different points, say x and y, we can use either left translations or right translations. So we can multiply this by either by y x inverse on the left or by x inverse y on the right. As a result, a topological group has two natural uniform structures, the left uniform structure and the right uniform structure. And this leads to two kinds of uniform continuity, given on this definition. In fact, many notions known from the theory of metric spaces can be extended to uniform spaces, and in particular to topological groups. In particular, we can speak of equicontinuous families of maps, about Cauchy sequences, about completion, completeness, about the completion, and so on. This notion, the notion uniform space, is sometimes it is useful, but it is too general for our purposes. And so we'll restrict to topological groups. That's all for today. As the next lecture, we'll begin by proving that if f is a continuous and compact supported function on a locally compact group, then it is both left and right uniformly continuous. This is a rather simple result from general topology. But it's quite useful from technical point of view, and in particular when we discuss representations of topological groups, it is very useful to know that every continuous compact supported function is left and right uniformly continuous. And then we discuss the uniform continuity, and then at the next lecture we'll begin to discuss the power measure on a locally compact group. So our next goal will be to show that on every locally compact topological group, there exists a very nice problem measure, which is invariant under left translations. This is the so-called left power measure. Okay, thank you.